Here's a question a child can answer. How many R's are in Raspberry? Ask the language model running on this machine. Llama 3.1, 8 billion parameters, no randomness. And it says 2. There are 3. It gets strawberry right. Now almost every model does, because the internet spent a year laughing about strawberry and the models read the internet. But raspberry? 2. Blueberry? 3. This isn't a counting problem, it's a seeing problem. The model never saw the letters. Before your question reaches the network, a small, separate program chops it into pieces and replaces each piece with a number. The word raspberry, with the space in front of it, is piece number 94,802. One piece. One number. There is no R in 94,802. That program is the tokenizer. It's the first thing that happens to everything you type. It decides how much you pay, how much the model can remember, what it can spell and what it can't, and almost nobody explains it. So let's explain all of it. What tokens are, the 3 ways to cut text, the algorithms that learn the pieces, the code, step by step, and which model uses which. This is going to be long. Let's go.
Inside AI. Tokenization. How a model reads. Every language model has the same front door. Text goes in, and the first stop is the tokenizer. It does one job. It owns a list, the vocabulary, and it cuts your text into pieces that are on the list. Each piece is a token. Each token's position in the list is its ID. That's it. The model downstream never sees text at all. It sees IDs, looks each one up in a table of numbers, we'll get to that table, and does its work. At the other end, the answer comes back as IDs, and the same tokenizer turns them back into text. Encode going in, decode coming out. 2 things to hold on to. First, the tokenizer is not a neural network. It's a list and a procedure, written before the model is trained, frozen forever after. Second, it's lossless. Encode, then decode, and you get back exactly what you typed, to the character. The only question is where the cuts go, and that question turns out to shape everything. The fastest way to see this is a small open-source web app called Tokenizer. It runs OpenAI's tokenizer library in your browser, and it can load the tokenizers of a dozen other models. Pick 040, the vocabulary GPT-4o and its successors use, and type, how many R's are in Raspberry? Every color is 1 token, the count on the right, 8, and underneath, the IDs, 5,299, 1991, and Raspberry, with its leading space, is 134,404, 1 chunk. Now watch the details, because they matter. Hello World, 2 tokens, and the space belongs to world, not to hello. That's the convention in this family. A words token usually carries the space in front of it. Capital H hello and small h hello are different tokens. Hello with a space in front is a third. Strawberry on its own is 3 pieces, stra, ah, berry. But with a space in front, it is a single token. Same letters, different cut, because the tokenizer learned the spaced version from millions of sentences and the bare version from almost none. Numbers, 1, 2, 3, 4, 5, 6, 7 becomes 1, 2, 3, 4, 5, 6, 7. Groups of 3 digits. Remember that, it comes back. 3 strawberry emoji, 6 tokens, 2 each. A word of Hindi, namaste, 4 tokens for 6 letters. Indentation in code, a whole run of spaces is a single token. Now switch the model. GPT-4, the same 8 pieces, different numbers. GPT-2 from 2019, 8 pieces again, but look at the IDs. Llama 2, 11. Raspberry is now 3 pieces, R, asp, berry, and the apostrophe is split from the S. Llama, 10. And pick a chat model, GPT-4o itself, and the app shows you something you never see, your message wrapped in tokens like imstart and imsep, the frame the model actually reads. 16 tokens before you said a word. Every one of these observations has a reason. By the end, you'll know all of them.
The app is a front end for a library.
and the library is 5 lines. Import tick token. Ask it for the O200K encoding. Encode the sentence. The list that comes back is the same 8 numbers the app showed, 5,299 through 30. Decode them and the sentence comes back, character for character. And one more line, N vocab, 200,019. That's the length of the list, the number of different pieces this tokenizer can produce. 200,000 is a choice somebody made. So is every piece on the list. Where do they come from? Nobody typed them in. They were learned by counting. But before the counting, there's a more basic decision. What should a piece even be? A word? A letter? Something in between? That's Chapter 2.
The obvious cut is the one you were taught in school. Words, split at the spaces. Here's the first paragraph of Alice in Wonderland. 57 words, 57 tokens. Clean. So let's build a vocabulary this way. We took 9 novels from Project Gutenberg: Alice, Frankenstein, Moby Dick, Dracula, Pride and Prejudice, and 4 more. 944,000 words of English. The number of different words in them, 27,360. And here's the first problem. 9,686 of those words, 35% of the vocabulary, occur exactly once in the whole pile. A third of the list is words we saw a single time, which is not enough to learn anything about them. Second problem. Take a 10th book the vocabulary never saw, Kafka's Metamorphosis, and 153 of its words are not on the list at all. Charlottenstrasse, unselfconsciously, chambermaids. A word-level tokenizer has exactly one move for them. Replace each with a single token that means unknown. The model reads a blank. Third problem. Run, runs, running, runner are 4 unrelated entries. The list doesn't know they share anything. The model has to rediscover it 4 times from scratch. And fourth, whole writing systems don't put spaces between words. Chinese, Japanese, Thai. Split at the spaces, and this sentence is 1 token. Words are how people read. They're a bad unit for a machine.
So go the other way. Cut at every character. The vocabulary collapses. Our 9 novels contain 116 distinct characters, and that list covers every word that will ever be written in English, including the ones nobody has invented yet. No unknowns. Ever. The price is length. That 57-word paragraph is 302 characters, 5 times as many tokens for the same meaning. And length is expensive for a transformer in a specific way. Every token attends to every other token, so the work grows with the square of the length. 5 times longer is about 25 times the attention. Worse, each token now carries almost nothing. The token T means nothing on its own. The model has to read 9 of them before it knows it's looking at raspberry, and reassemble the word inside itself before it can think about it. Characters are cheap to list and expensive to think in. There's one more version of this idea that matters later. Go below characters to bytes. Unicode has about 155,000 characters. Bytes? 256. Hold that thought.
The answer every modern model uses sits in between, and it's called subword tokenization. The rule is simple to state. Common words stay whole. Rare words are cut into pieces that are themselves common. The paragraph again, cut the way GPT-4 cuts it. 67 tokens for 57 words. Almost every word is 1 piece. Peeped is 3. Unhappiness becomes unhap-iness. Tokenization becomes tokenization, and ization is a piece the model will meet again in organization, civilization, realization. Anti-disestablishmentarianism, 6 pieces, every one of them reusable. Nothing is unknown. In the worst case, the pieces shrink to single letters, and in the best designs to single bytes. And the sequence stays short. Across an entire held-out novel, GPT-4's tokenizer spends 1.23 tokens per word, about 4 characters per token.
That's the number behind the rule of thumb that a token is roughly 3/4 of a word. Here is the question the rest of this film is about. Who decides the pieces? Not a linguist. Nobody sat down and wrote isation on a list. An algorithm did, by counting. And the most important one was invented for a completely different purpose 30 years ago.
In 1994, a programmer named Philip Gage published a short article in the C Users Journal. He wanted to compress files. His idea: scan the data, find the pair of bytes that occurs most often, replace every occurrence of that pair with a single byte that isn't being used, write down the substitution, and repeat. He called it Byte Pair Encoding. It was a compression trick, and it sat quietly for 20 years. Then, in 2015, Rico Senrich, Barry Haddow, and Alexandra Birch at the University of Edinburgh were building translation systems and kept hitting the unknown word wall we just saw. Their paper, Neural Machine Translation of Rare Words with Subword Units, took Gage's loop and pointed it at text. Don't compress the file, learn the vocabulary. Merge the most frequent pair of characters again and again, and the merges you collect are your pieces. That is still essentially what GPT-4, Llama 3, Qwen, and DeepSeek run on today. Let's build it.
Here's the whole algorithm in one picture. A corpus, 5 words with counts. Cat, 6 times. Cats, 3. Hat, 4. Hats, 2. Chat, 5. Step 1. Split every word into characters. Our starting vocabulary is just the letters A, C, H, S, T. 5 tokens. Step 2. Count every adjacent pair, weighted by how often its word occurs. A followed by T. That pair appears in every word. 6 plus 3 plus 4 plus 2 plus 5. 20. H followed by A. 11. In hat, in hats, and inside chat. C followed by A. 9. T followed by S. 5. C followed by H. 5. Step 3. Take the winner, AT, and merge it everywhere. Every AT becomes one symbol, at. Add at to the vocabulary. 6 tokens now. Step 4. Go back to step 2. That's it. That's byte pair encoding. The only decision left is how many times to loop, and that number, the number of merges, is what sets the size of the vocabulary. GPT-4's vocabulary is 100,000 merges. Ours will be 5. Let's write it. Here is the training side, and it's short enough to read every line. The corpus is a dictionary, each word as a tuple of its characters mapped to its count. Cat is the tuple CAT with a 6. Count pairs. Make a counter. For every word and its count, zip the symbols with the same symbols shifted by 1. That pairs each symbol with its neighbor, C with A with T. And for each pair, add the word's count. Return the counter. That's step 2. Merge word. Given one word symbols, a pair, and the new symbol, walk from the left with an index. If the 2 symbols at the index are the pair, emit the new symbol and skip 2. Otherwise, emit the 1 symbol and move 1. Return the rebuilt tuple. Merge. The same for the whole corpus. The new symbol is just the 2 strings glued together, and a dictionary comprehension rebuilds every word. That's step 3. Train. Turn the corpus into tuples. Keep a list of merges. Loop num merges times. Count the pairs. Take the one with the biggest count. Merge it everywhere, remember it. The list you return is the vocabulary, in the order it was learned. And that order, the rank of each merge, is what the encoder will need. 28 lines. That is the algorithm inside GPT-4's tokenizer. Theirs is written in Rust and runs on Bytes, but it is this loop. Run it. Step 1. The table. AT 20. HA 11. CA 9. TS 5. CH 5. Merge AT. Every word changes. C at S, H at, H at S, CH at. Step 2. Count again. And notice the table is different now, because the symbols are different. H followed by at, 4 plus 2 plus 5, 11. C followed by at, 9. At followed by S, 5. C followed by H, 5. Merge H at. Now hat is one symbol. In hat, in hats, and inside chat, which is C hat. Step 3. C at, 9. Chat, 5. At, 3. Hats, 2. Merge C at, cat. Step 4. Chat, 5. Cats, 3. Hats, 2. Merge C at, chat. Notice what just happened. Chat was built from C plus hat, not from CH plus at, because hat was learned first. The history of the merges decides the pieces. Step 5. Cats, 3. Hats, 2. Merge cats S, cats. And stop. 5 merges, as promised. Our vocabulary: A, C, H, S, T, at, hat, cat, chat, cats. 10 tokens. It never learned hats. 2 occurrences wasn't enough to win a round in 5. Frequency decides everything. The whole vocabulary of GPT-4 is this table, run 100,000 times over a slice of the internet. Nothing else.
Why the most frequent pair, and not say the pair that makes the nicest word? Here's the arithmetic, and it's the whole justification. Count the symbols in our corpus. Cat has 3 times 6, 18. Cats 12, hat 12, hats 8, chat 20, 70 symbols. Now merge a pair that occurs C times. Every occurrence turns 2 symbols into 1, so the corpus shrinks by exactly C. Merge at 20 occurrences, 70 becomes 50. Merge H at 11, 39. C at 9, 30. CH at 5, 25. Cat S 3, 22. 70 symbols became 22, 3.2 times fewer, and each step shrank the corpus by exactly the count in the table. So most frequent pair means the merge that shortens the corpus the most right now. BPE is greedy compression. That's why Gage invented it for files, and it's why it works for language models. The model reads fewer, richer units. Greedy, not optimal. It never looks 2 merges ahead. And it's the same number we measured at scale, tokens per word falling from 2.2 to 1.2 as the vocabulary grows. That curve is this subtraction, repeated 30,000 times. One more thing the arithmetic tells you. The first merges are worth a lot, 20, 11, and the last one's almost nothing, 3. That's why the curve flattens.
Encoding a new word uses the list you trained. Give every merge its rank. At is 0, hat is 1, cat 2, chat 3, cats 4. Start from the word's characters. Look at every adjacent pair and pick the one with the lowest rank, the earliest merge you learned. If none of the pairs is in the list, stop. Otherwise, merge it and look again. Chats, a word the tokenizer never saw. CHATS. The pairs, CHATS. AT has rank 0. Merge. CH at S. Now H at rank 1. Merge. C hat S. Now C chat rank 3. Merge. Chat S. And chat S. Never learned. Stop. Chats is chat plus S, 2 tokens, and their IDs are their positions in the list, 8 and 3. That's what the model receives. Cast. C-A-S-T. C-A, not a merge. A-S, no. S-T, no. 4 letters, 4 tokens. The tokenizer has never metacast, so it spells it out. No error, no unknown, just a longer sequence. That, exactly, is what happened to Charlottenstrasse. And decoding is trivial. Look up each ID, glue the strings. That's the whole tokenizer. Train once, then encode and decode forever. Now, the real thing. The same algorithm in a library, Hugging Faces tokenizers, written in Rust, on our 9 novels, 5 million characters.
3 lines, a BPE model, split on white space first. Trained to 1,000 pieces. It takes half a second. Watch the first merges, TH, IN. Then the third merge already makes the, AN, ER, OU, RE, AT. By merge 13, and, merge 16, ing. Nobody told it English has suffixes. The counts did. Now the trade. Train to different sizes and measure the same held-out novel. 300 pieces, 2.2 tokens per word. 1,000, 1.6. 3,000, 1.35. 10,000, 1.2. 30,000, 1.18. GPT-4's 100,000, trained on vastly more text, gets 1.235 on the same book. The curve flattens fast. Each doubling buys less, which is why vocabularies are tens of thousands and not millions. And watch Raspberry. At 300, it's R, as, PAS, BER, RE. At 30,000, Raz, PAS, Berry. Still not one piece, because Raspberry appears exactly 0 times in these 9 novels. A token exists only if its text was common in the training data. One confession. The straight apostrophe in our question is unknown to this tokenizer. 19th century typesetting uses curly quotes, so the straight one never appeared, so it has no token. One unknown from a single character. That's the hole the next idea closes.
In 2019, the GPT-2 paper made one change to Senrich's recipe that every large model since has copied. Don't start from characters, start from bytes. Every piece of text in every script is a sequence of bytes in UTF-8. A is 1 byte, A is 2. A Chinese character is 3. The strawberry emoji is 4. So make the 256 possible byte values the base vocabulary and run the merges on top of that. Now, nothing can be unknown, ever. Not an emoji, not a language you forgot to include, not a straight apostrophe. At worst, it costs a few tokens of raw bytes. That's why the emoji is 3 tokens in GPT-4 and 2 in GPT-4o. They're byte pieces, not picture pieces. There's a small wrinkle you'll meet if you ever open a vocabulary file. Bytes like a space or a new line aren't printable, so GPT-2 maps every byte to a visible character for storage. A space becomes a capital G with a dot, a new line a C with a dot. When you see that G.Raspberry in a vocabulary file, the G is the leading space. SentencePiece, which we'll meet soon, solves the same problem differently. Llama 2 keeps real characters in its vocabulary and falls back to bytes only when it has to. The emoji becomes 4 tokens, 1 per byte, written as hexadecimal. Llama, with its enormous vocabulary, has the emoji as a single token, and BERT from 2018, with no byte fallback at all, gives up. Unknown.
One more piece of the machine, and it's the one that explains the numbers. Before BPE ever runs, the text is chopped by a regular expression into chunks: words, numbers, punctuation, runs of spaces, and mergers are only allowed inside a chunk. Here is GPT-2's actual pattern. It peels off contractions, V, tunt, S, as their own chunks. It takes a run of letters with its leading space, a run of digits with its leading space, punctuation, white space. That's why a token almost always starts with a space and never crosses from a word into a comma. Now GPT-4's pattern: 2 changes, contractions match in any case, and digits, at most 3 at a time. So 1, 2, 3, 4, 5, 6, 7 can't be a chunk. It's 1, 2, 3, 4, 5, 6, 7, before BPE even looks at it. GPT-2 had no such rule, and its mergers learned whatever the data offered. 1, 2, 3, 4, 5, 6, 7. Arbitrary. Llama 2, Gemma, and Quen went the other way. Every digit is its own token, always. 3 philosophies for numbers, all set by one line nobody sees. When we get to arithmetic, this line is the reason. One last look. The O200K pattern, longer and uglier, and notice it now keeps IVE as a single chunk. That's the whole machine. A regex into chunks, bytes underneath, mergers on top. Everything in the GPT family is that.
Before the other families, a look inside the two libraries you'll actually use. TikToken, OpenAI's, is almost nothing but a data file. OpenCL100K's file, and here is what's in it. 100,256 lines. Each one a token's bytes in base 64 and its rank. Line 0, an exclamation mark. Line 1, a double quote. Rank 94,802, space raspberry. The rank is the ID. The order the merges were learned is the numbering of the vocabulary. The encoder applies the regex, then merges lowest rank first, exactly as we wrote it. Theirs is in Rust. Special tokens, end of text and 4 others, live outside the file, and encode refuses them by default. You have to say allowed special. Otherwise, the text end of text is cut into ordinary pieces. Encoding for model maps a model name to its file. GPT-4 to CL100K, GPT-4o to O200K. Hugging Face's tokenizers library is the one most open models ship with, and its heart is a JSON file, tokenizer.json, with 5 stages in a fixed order. Normalizer, clean the text. BERT lowercases and strips accents here. Llama 3 does nothing. Pre-tokenizer, chop into chunks. The regex, then the byte mapping. Model, BPE, WordPiece, or Unigram. The vocabulary and the merges live here. Llama 3's has 280,000 merges. Post-processor, add the frame. BERT's CLS and SEP. Llama's begin of text. Decoder, undo the byte mapping. 3 lines of Python, load the file, encode the sentence, and you get tokens, with the G dot for spaces, and IDs. Decode gives the sentence back. And the wrapper most people use, Transformers Auto Tokenizer, does the same with one extra move. It adds the begin of text token at the front, so the same sentence comes back as 9 IDs, not 8. Its apply chat template turns a list of messages into the framed token stream we'll meet in Chapter 5. That's the toolbox. Now the other families.
Google got to the same place by a different road. In 2012, Mike Schuster and Keisuke Nakajima needed a vocabulary for Japanese and Korean voice search, languages without spaces, and built WordPiece. It became famous in 2018 as the tokenizer inside BERT, 30,522 pieces. The loop is the same as BPE. Start from characters, merge, repeat. 2 things differ. First, how the winner is chosen. BPE picks the most frequent pair. WordPiece picks the pair with the highest score, the count of the pair divided by the count of its first part times the count of its second. Read it as, how much more often do these two appear together than you'd expect from how common each one is? It's a likelihood ratio. We'll take it apart in a moment. Second, a convention. A piece that continues a word is written with 2 hashes in front, hashization, so you can tell it from a piece that starts one. Watch the difference on our toy corpus. BPE's first merge was at 20 occurrences. WordPiece's first merge is C followed by #H. Only 5 occurrences, but an H inside a word appears in exactly one word here, chat, so every single one of them sits next to a C. 5 over 14 times 5, 0.07. At scores 0.05. Frequent, but A and T are everywhere. The rare but faithful pair wins. Encoding is different too, and simpler. There's no merge list. Take the word, find the longest prefix that's in the vocabulary, cut it off, repeat on the rest with the hashes. Raspberry against BERT's real vocabulary. Raspberry? No. Raspberry? No. Down, rasp? No. Ras? Yes. Then #berry, #bear, #p? Yes. Then #berry? Yes. 3 pieces, 14 tries. And BERT lowercases everything and strips accents before it starts. Cafe becomes cafe. Naive becomes naive. Cheap, and it's why BERT cannot tell Apple the company from Apple the fruit by the capital letter.
Let's take the score apart, because it hides a nice idea. Divide every count by n, the total number of symbol occurrences, 70 in our corpus, and counts become probabilities, p of a symbol, p of a pair. Now the score, count of the pair over count of A times count of B, is the same thing as the probability of the pair divided by the probability of A times the probability of B, up to the constant n. And that ratio has a plain meaning. How many times more often do A and B appear together than they would if they were independent? 1 means no more than chance. 5 means 5 times more than chance. For C and hash H, 5 over 14 times 5 times 70, 5. An H inside a word sits next to a C 5 times more often than chance predicts. For A and T, 20 over 20 times 70, 3.5. Frequent, but less surprising. Take the logarithm and you have what information theory calls pointwise mutual information. Log of 5 is 1.6. Log of 3.5 is 1.25. So WordPiece merges the most surprising pair, the one whose parts are most faithful to each other. And here's the honest footnote. Schuster and Nakajima's paper says, pick the merge that raises the likelihood of the training data the most. The total gain is the count of the pair times that log. 5 times 1.6 is 8. 20 times 1.25 is 25. By the total, AT wins, as in BPE. By the ratio, which is the score as it's usually taught, CH wins. Same idea, 2 readings, and the vocabulary you get depends on which one you pick. Now the third algorithm turns the whole thing into probabilities from the start.
Taku Kudo at Google in 2018 turned the whole thing upside down. BPE and WordPiece grow a vocabulary from the bottom. Unigram starts with far too many pieces and cuts. Begin by listing every substring that occurs in the corpus. On our toy data, 17 candidates, from single letters up to whole words, and give each a probability, its share of all the occurrences. Now the model. A word's probability is the product of its pieces' probabilities, and its tokenization is the segmentation with the highest product. Chats has 15 possible segmentations under that candidate list. C-hats, ch-hats, chat-hats, chatsa, all the way down to single letters, and the best one is the one you'd keep. Here's the code. List every segmentation recursively and take the one whose product is largest. Training is 2 moves repeated. First, improve the probabilities. For every word, look at all of its segmentations, weigh them by their probability, and count how often each piece gets used, expected counts. Then renormalize. That's EM. Second, prune. For each piece, ask how much worse the corpus would score if you deleted it. Here are the real numbers. Deleting at costs nothing. It helps slightly because every word has a better route without it. Ka, ats, ha, nearly free. Deleting cat costs nearly 30 units of log likelihood. Hat, 27. Chat, 11. So the cheap ones go, the expensive ones stay, and you repeat until you're down to the size you wanted. 12 pieces in our case. Cat, chat, hat, cats, hats, and the letters. Chats is chat plus S. Cast is spelled out. 2 things make Unigram special. Because it's probabilistic, it can give you the second best segmentation too, and during training you can sample them. Kudo called it subword regularization, and it makes models more robust to odd spellings. And it's the engine inside SentencePiece's default mode, which is why T5, Albert, XLNet, and XLM Roberta all read text this way.
The mathematics of Unigram is the cleanest of the 3, so let's do it properly. The model says a word is a sequence of pieces drawn independently, so the probability of a word is the product of its pieces' probabilities. Products of small numbers get tiny, so we work with logs. The log probability of a word is the sum of the log probabilities of its pieces. Start from counts. 160 substring occurrences in our toy corpus, so P of C is 14 over 160, P of hats, 2 over 160, P of chat, 5, P of S, 5. Chats as C plus hats, 0.0875 times 0.0125, about 1 in 900. Chats as chat plus S, about 1 in 1,000. Both tiny, C hats wins, by a little. Add up all 15 segmentations and you can turn them into shares. C hats carries 22% of the probability, the next 3, 19% each. Those shares are what the E step uses. Expected counts. For every word in the corpus, every segmentation contributes its share to each piece it contains, sum over the corpus, and that's how often each piece is really used. The M step divides by the total, new probabilities. Then the loss, the number training drives down, is minus the sum over words of frequency times the log probability of the best segmentation. R starts at 66, drops to 42 after 1 EM step, 33 after 2.
Pruning, as we saw, asks for each piece what that loss becomes without it and drops the cheapest. And best segmentation, the Viterbi step, is just the maximum over segmentations of the sum of logs. Our code lists them all because our words are short. The real thing does it with dynamic programming in one pass. Products, logs, expected counts, a loss. That's Unigram.
SentencePiece, also Kudo with John Richardson later in 2018, isn't a new algorithm. It's the toolbox that made the algorithms practical, and it made 3 decisions that shaped half the models you use. 1. Treat the text as a raw stream. No pre-tokenization, no assumption that spaces separate words. The space is just another character, written as a low line. So Japanese, Chinese, and Thai are handled exactly like English, and decoding is lossless by construction. 2. It trains either BPE or Unigram on that stream, your choice, with 1 line. Here it is on our 9 novels, 8,000 pieces, 4.5 seconds for Unigram, under a second for BPE. 3. It ships as 1 small model file that every framework can load. Look at the hero sentence through the 2. Unigram says ra, sp, air, berry. BPE says rasp, bear, re. Same corpus, same size, different pieces, because the 2 algorithms optimize different things. And here's the map of the world today. On one side, the SentencePiece family, T5, Llama 1 and 2, Mistral 7b, Gemma, and per Google's own report, Gemini. On the other side, the GPT family, Bytes, a regex, and BPE, GPT-2 through GPT-4o, and since 2024, Llama 3, Qwen, DeepSeek, Mistral's Tekken, 5.4. 2 families. And in the last 2 years, almost every new open model crossed to the second. Why, and with what vocabulary sizes, is the next chapter.
Which model uses which? Here's the table, and every number on it was read from the model's own tokenizer file this morning, not from a blog post. GPT-2 and GPT-3, byte level BPE, 50,257. GPT 3.5 and GPT-4, the CLOW 100K vocabulary, 100,277. GPT-4o, the O series, GPT 4.1, O200K, 200,019. OpenAI's OpenWeight GPT-OS, the same list plus 1,000 control tokens for its chat format, 201,000. BERT, WordPiece, 30,522. T5, SentencePiece Unigram, 32,100. XLM Roberta, multilingual, Unigram, 250,000. Llama 1 and 2 and Mistral 7b, SentencePiece BPE, 32,000 each with byte fallback. Llama 3 switched families, TikTok style, 128,000, of which 256 are reserved control tokens. Mistral's newer Tekken, 131,000. Qwen 2.5 and Qwen 3, 151,000. DeepSeek v3, 128,000. 5.4, 100,000, built on Cloud 100. Gemma 3, SentencePiece, 262,000, the largest here, and Google's report says Gemini uses the same one. And Claude, Anthropic has not published its tokenizer. You can count tokens through their API. You cannot see the pieces. We'll say that plainly rather than guess. 3 families on one table, WordPiece, SentencePiece, byte level BPE, and a number that has grown from 30,000 to 260,000 in 7 years.
Same sentence, 11 tokenizers. Count the pieces. GPT-2, 8. GPT-4, 8. GPT-4o, 8. Llama 2, 11. Raspberry in 3, the apostrophe split off. Llama 3, 8. Tekken, 9. Raspberry. Gemma, 9. Qwen, 8. DeepSeek, 9. BERT, 11. Lowercased with its hashes. T5, 10. Now look at 2 of the rows, GPT-4 and Llama 3, not at the pieces, at the numbers underneath. 4,438, 1690, 436, 596, 527, 304, 94,802, 30. Identical. Every ID. That's not a coincidence. Meta's Llama 3 paper says its vocabulary combines 100,000 tokens from OpenAI's TikToken with 28,000 of its own for other languages, and the first 100,000 are literally the same list, in the same order. 2 of the most used models on Earth read English with the same dictionary. We checked it against the actual model file on this machine. The Llama 3.1 weights in a Llama carry a vocabulary of 128,256 entries, and they tokenize the question to those same 8 numbers.
Why did the number grow? Put the vocabularies on a timeline. 30 to 50,000 in 2018 and 2019. 100,000 in 2022. 128, 150, 200,000 in 2024. 262 in 2025. The reason is in the multilingual numbers we'll see in a moment. A bigger list means more whole word pieces for more languages. So the same text costs fewer tokens, cheaper, faster, and more of it fits in the context window. So why not 10 million? Because every token is a row in a table. The model's first layer is a matrix, 1 row per token. Each row as wide as the model. The embedding table, the subject of the next episode. GPT-2, 50,000 rows times 768. 38 million numbers, 31% of the whole model. Llama 3.1, 8 billion. 128,000 rows times 4,096. 525 million parameters, 6.5%. Llama 3's smallest model, 1 billion parameters, with its 262,000 rows. 300 of them are the table. Almost a third of the model is vocabulary. And a wider vocabulary also means the last layer, the one that scores every possible next token, gets wider too. And each rare token gets fewer training examples. So the number is a trade. Sequence length against table size, against how much data each piece sees. Nobody has found the bottom of that trade yet. The trend says bigger.
Some tokens are not text. Llama 3's vocabulary ends with 256 special entries: begin of text, end of text, start header, end of turn, and a long run of reserved slots. They can never be produced by tokenizing your input. Type the characters and they'll be cut into ordinary pieces. Only the model's own software inserts the real ones. Here's what a chat actually looks like to Llama 3.1, rendered with its own template. Begin of text, start header, system, end header, the system prompt, end of turn, start header, user, your question, end of turn, start header, assistant. 35 tokens, of which 15 are your words. The rest is scaffolding the model was trained to read as structure. Qwen uses im_start and im_end, Gemma, start of turn and model. OpenAI's GPT-OSS, start, channel, message, end. The app showed us this earlier with GPT-4o's im_start and im_sep, the same idea. Why does this matter to you? 3 reasons. The frame costs tokens, you pay for them. The model's sense of who is speaking is entirely these tokens, which is why text that imitates them can confuse it. And when a model is fine-tuned into a chatbot, what's really being taught is what comes after that last assistant header. Now, what do all these cuts do to the model?
Now go back to the opening. How many R's are in Raspberry? The model receives token 94,802. To answer, it has to know how that token is spelled, and nothing in its input tells it. It has to have memorized the spelling of that piece, the way you memorize a phone number, from the places in its training data where the word was spelled out, or rhymed, or split. For strawberry, since 2024, those places are everywhere. It became a running joke, and the joke went into the training data, so strawberry is fine. Here's the honest table from this machine, temperature 0. Llama 3.1 gets strawberry, cranberry, gooseberry, elderberry, and mulberry right, and raspberry, blueberry, and blackberry wrong. Qwen 3 gets raspberry right, and mulberry and blackberry wrong. Different models, different memorized spellings, same cause. And the same cause sits under every AI can't spell story.
reversing a word, counting its letters, rhymes, anagrams, syllables. The model isn't bad at them, it's blind to them. Modern systems work around it. They write a tiny program or reason step by step until the word is spelled out in pieces. But notice what the workaround is. Spell the word into smaller tokens first. Tokenization was always the problem.
Numbers get the same treatment, and the consequences are stranger. 1, 2, 3, 4, 5, 6, 7. GPT-2, 1, 2, 3, 4, 5, 6, 7. Whatever merges its data happen to produce. GPT-4 and Llama 3, 1, 2, 3, 4, 5, 6, 7. The regex's rule of 3. Llama 2, Gemma, Quen, 1 digit per token. Now add 12,345 plus 67,890. In GPT-4's tokens, that's 1, 2, 3, 4, 5 plus 67890 equals 80235. Look at the columns. The pieces of the answer don't line up with the pieces of the inputs. The ones digit of the first number shares a token with the tens digit, and in the answer it doesn't. The model has to learn arithmetic across boundaries that move from number to number. With 1 digit per token, every column is its own token and the alignment is trivial, which is one reason digit per token was a deliberate design choice in Llama 2 and Gemma. Or the famous comparison, which is bigger, 9.11 or 9.9? Tokenized, 9.11 is 9.11. 9.9 is 9.9. 11 is bigger than 9. Unless the model has learned that the token after the point is a fraction, it will compare the pieces, and many did. None of this is arithmetic. It's all in the cut.
Here's the same sentence, the first article of the Universal Declaration of Human Rights, in the official translations, in 10 languages, through 4 tokenizers. English, 33 tokens in all of them. French, 50 in GPT-4's vocabulary. Russian, 74. Arabic, 91. Hindi, 180. Same meaning, 5.5 times the tokens. In GPT-2's vocabulary, Hindi is 294, every letter costing several byte tokens because the vocabulary had almost no Devanagari in it. Now the newer lists. GPT-4o's 0200K, Hindi drops to 54, Russian to 41, Arabic to 44. Gemma's 262,000, Hindi 45, almost English. This is what the bigger vocabularies bought, and it isn't cosmetic. Tokens are what you pay for, per million. Tokens are what fills the context window. Tokens are what the model generates one at a time, so their speed. A Hindi speaker using GPT-4 paid 5 times more per sentence, got 1/5 of the effective context, and waited 5 times longer for the same answer, a tax that existed entirely inside the tokenizer. Llama 3's 28,000 added tokens were for exactly this. Hindi goes from 180 to 93. Not solved. Halved. And look at Japanese. Still 71 tokens in 0200K for 84 characters. The tokenizer is where a model's language priorities are written down, in numbers, before training starts.
Code has its own tax, and it was fixed on purpose. This 6-line function, 115 characters. GPT-2, 59 tokens. GPT-4, 34. Same text, GPT-2 spends nearly twice as much. Look where it goes, the indentation. GPT-2's regex and merges treat each space as its own token. 4 spaces, 4 tokens. A line indented 8 deep costs 8 before the word even starts. CL100K has tokens for runs of spaces. The same line costs 1 token for the run plus 1 for the word. New line plus colon, open paren plus word, merged. When OpenAI built CL100K in 2022, the training text had far more code in it, and the merges learned that. It's one of the quiet reasons GPT 3.5 was so much better at programming than GPT-3. It could see nearly twice as much code in the same window. Llama 2, with SentencePiece, sits in between at 39, Gemma the same. So if you ever wondered why the same prompt costs different amounts on different models, the answer is usually spaces.
In February 2023, 2 researchers, Jessica Rumbelow and Matthew Watkins, were probing GPT-3's vocabulary and found tokens that made the model behave strangely. It would refuse to repeat them, or answer with an unrelated word, or insult you. The most famous was SolidGoldMagikarp. Look at it in GPT-3's vocabulary. 1 token, ID 43,453. A Reddit username. The tokenizer had been trained on a scrape that included a forum, where a handful of users had posted millions of times, counting to infinity, one post at a time, so their names were frequent enough to earn a token. But the model's training data was filtered differently, and that forum was mostly gone. The token existed, the model had almost never seen it. Its row in the embedding table was never properly trained, essentially random, and the model fell apart when it met it. The lesson is precise. The tokenizer and the model are trained separately, on different data at different times. A token's existence tells you about the tokenizer's data. Its meaning comes only from the models. The two can disagree. In the 100,000 token vocabulary that followed, SolidGoldMagikarp is 5 ordinary pieces: solid, gold, mag, ic, arp, and the glitch is gone. Not fixed in the model, fixed in the cut.
So why have tokens at all? Every problem in this chapter came from them, and researchers have been trying to remove them. Byte 5 in 2021 fed raw bytes to a transformer, no vocabulary, and it worked, at the cost of sequences several times longer and slower training. Megabyte in 2023 and Meta's byte latent transformer at the end of 2024 attacked the length problem directly. Read bytes, but group them into patches on the fly. Long patches where the text is predictable, short ones where it isn't. So the expensive part of the model runs on far fewer units, and the boundaries are learned instead of frozen. The BLT paper reports matching Llama 3 at 8 billion parameters, with no tokenizer at all. None of these is what you use today. But they tell you what tokenization is, not a truth about language, an engineering compromise between a sequence that's too long and a table that's too big. And for now, every model you talk to lives inside that compromise.
Here's what we learned in 10 lines. 1. The model never sees letters. It sees a list of numbers, the token IDs. 2. A tokenizer is a list plus a procedure, the vocabulary and the rule for cutting, decided before training, frozen after, and lossless. 3. There are 3 ways to cut. Words leave unknowns and hide morphology. Characters are 5 times longer and cost the square of that in attention. Subwords are the compromise every modern model uses. 4. Byte Pair Encoding learns the subwords by counting, merge the most frequent pair, repeat, which is greedy compression. Encoding replays the merges by rank. We wrote it in 28 lines, and it is GPT-4's logic. 5. Start from bytes, not characters, and nothing is ever unknown. A regex decides how numbers, spaces, and contractions are chunked, and that one line shapes arithmetic and the cost of code. 6. WordPiece merges by surprise rather than count, and encodes by longest match. Unigram starts huge and prunes with probabilities, EM and Viterbi. SentencePiece is the toolbox that runs either on raw text, and the world splits into its family and the GPT family. 7. Who uses what? 30,000 tokens in 2018, 262,000 in 2025. Llama 3 literally shares GPT-4's IDs. Claude's is unpublished. 8. A vocabulary is also a table. Vocabulary times width. A third of GPT-2, a third of a small Llama, so its size is a trade. 9. Chats are framed by special tokens. The model reads a structure. 10. Spelling, arithmetic, the multilingual tax, indentation, glitch tokens, every one of them lives in the cut, not in the model. If you remember one sentence, the tokenizer decides what the model can see.
Let's end where we began. How many R's are in Raspberry? 8 tokens, 8 numbers, 4,438, 1690, 436, 596, 527, 304, 94,802, 30. That's what the model sees. We now know where the numbers come from. A list of 100,000 pieces, learned by counting pairs in a mountain of text, chopped by a regex, built on bytes. And we know what the list costs, in spelling, in arithmetic, in languages, in code.
But a number is just a name. 94,802 is not Raspberry, any more than your phone number is you. Inside the model, that ID does exactly one thing. It selects a row in the table, 4,096 numbers, in Llama 3. And those 4,000 numbers are what the model actually thinks with. What's in the row? How does a machine learn that Raspberry is near Strawberry and far from Spreadsheet, from nothing but the company a token keeps? That's embeddings. That's the next episode.